Okay, hi everyone. This is Ken 422, Chemical Reaction Engineering, week number 2. So in this week, we'll talk about ideal batch reactor kinetics. Just a reminder that homework number 1 is due on September 1st, and homework number 2 will be assigned. It's available on Blackboard, and the solutions will also be posted in a video. So if you recall from the last lecture, we're just talking about basic chemistry things. Reaction order, stoichiometry, things like that. Very basic. And now we're going to start talking about the real reaction engineering, starting to get into it. Okay. So this chapter or this lecture is titled Interpretation of Batch Reactor Data. And this lecture is basically taken from the book by Levenspiel, chapter 3. It's been posted as part of your reading material for this week, so it's usually good to have it as a reference in case you want some more explanation, want to look at some intermediate steps in the derivation. You can always look at that book, and your homework is taken from that book, so I'm using that book extensively for this course. So let's start off by talking about what is a batch reactor. And a batch reactor is basically a vessel where I charge in all my reactants, let it sit for a certain amount of time, maybe do some mixing, maybe do some heating, whatever, and then take out my products once it's done. This is as opposed to a continuous flow reactor where I have reactants going in, reacting, and taking products out all the time. And a batch reactor is a piece of equipment in which empirical information is obtained for reaction kinetics, right? So usually if you want to understand the kinetics of a reaction, most of the time you'll do it in a batch reactor and look at the change of concentration with time, maybe look at the change of conversion with time, and this is how you really understand the reaction kinetics, okay? And usually when dealing with batch reactors, we have a bunch of initial assumptions. The first one is that our mixture has a constant density, and this is valid for almost all liquid phase reactions or for most liquid phase reactions. And by this, what I mean is that my volume in my reactor is fixed, or the volume of the fluid in my reactor is fixed, so the density in my reactor is fixed. And this is simplification to simplify interpreting this data and analyzing this data. So in the cases where my, let me change this pointer here. In the cases where my density is fixed, my reaction rate, if you recall from lecture 1, the reaction rate is basically minus or R, I have a product, is 1 over V dN by dt. So this is reaction rate in terms of volume. And dN by dt is the change in number of moles. If I assume that my volume is constant, I can move it up into this guy. So I get d of Ni by V by dt, and this is just the concentration. So what I'm looking for when looking at my experimental data from a batch reactor, and I'm trying to get some kinetics, I need to look at the change of concentration versus the change in time. And in cases where temperature is constant, or if I have a gas, you can always use the ideal gas law to do some manipulations. So, if I have a gas phase and its temperature is constant, I can change my N over V to, N over V can be substituted to P over RT. R is your constant, T is constant if you're running your experiments isothermally, and your reaction rate just becomes Ri is equal to 1 over RT, it's the fixed number dP by dt. So now we can monitor the change of partial pressure versus time, and this will give you the information about the kinetics. Okay, so let's say you did your experiments in a batch reactor, you have a bunch of points, and you want to interpret them, you want to, do your analysis on them. How do you do it? There are 2 main ways to do it, or 2 main approaches. First method is called the integral analysis, and this is what we will be covering in this course. And in the integral analysis, you just make a guess on the form of the rate equation, and then once I have my rate equation, Ri is equal to dC by dt, I integrate this expression to get an equation which just C as a function of T, or T as a function of C, right? Where I just have my 2 components, concentration and temperature, without any differential type format. And once I get this expression, I compare it to my experimental data and see if it matches. And then to see if your equation matches, you need to do some statistical metrics, which you took in, I think, 2-to-1 or whatever it is. This won't be the focus of our course, or we won't really deal with data analysis, but you just need to know that if it's a straight line and your experiments are a straight line, they need to match somehow with the slope. You might need to do some nonlinear regression like r squared, whatever it is, to try and see if does this equation match these points or not. Okay, so this is called integral analysis. The other form is called differential analysis. And in differential analysis, I'm just trying to compare my data to my dc by dt expression, right? So this will involve me calculating the slopes, because dc, change of concentration, change of time. And basically, I'm trying to match the slope of my experimental data to this rate expression, which is dc by dt. And this method can be better when you have large amounts of data. However, you're susceptible to having a lot more noise. So for example, if you have measured 2 points or 1 point is off, your slope is completely off, and this will result in a huge deviation. It might result in a huge deviation in your analysis, or might introduce a lot of noise into your analysis, okay? So just to recap the two methods, integral analysis, where I'm taking my rate expression here, R is equal to dc by dt. I'm integrating this expression to get c as a function of t, or t as a function of c, where I just get one straight nice equation and comparing this equation to the experimental data. Second method is called differential analysis, where I'm directly comparing my experimental data to the differential form. So I'm converting my experimental data to a dc by dt format by plotting and calculating the slopes, and then comparing the slopes to this dc by dt expression. And again, in this course, in this chapter, we're only dealing with integral analysis. Differential analysis is something you can pick up by experience, and there's not much to it. Okay. So when it comes to integral analysis, we have a bunch of cases, right? So you have experimental data, and you want to compare it versus some set of kinetics, right? So you need to compare it versus these 7 or 8 cases, which I'm gonna talk about, okay? The first case, it's when you have an irreversible unimolecular first order reaction, where I have A going to K, unimolecular, just one molecule, going to products, first order, 1 mole, 1 mole, irreversible, just goes to completion. This is case 1. And the assumptions we're gonna have here, constant volume, constant temperature, elementary, right? And again, when you're solving a problem, I expect you to write these assumptions to show me that you have the mental awareness of these details, right? So let's say I have this reaction. I have A reacting at a reaction rate constant of K to give me some products. What's my reaction rate? If you recall, or minus RA is equal to minus dCA by dt. And again, this minus is because A is a reactant, and minus dCA by dt is equal to KCA. And this is from your stoichiometry, from your chemistry, whatever it is. The rate of consumption of A is equal to KCA, right? So if I rearrange this, I'm just gonna move my CA to this side and move my dt to this side, just lumping the variables together. I get minus dCA divided by CA is equal to K dt. So again, you have my reversible unimolecular first order reaction. This is my reaction rate. Minus dCA by dt is equal to KCA. I separate my variables, so I move my CA and dCA together, and I move my dt to the other side. K is a constant, so it doesn't matter. And I get this expression. So now, integral method, I'm going to integrate this expression to get an equation of CA in terms of T. That's what I do here. So I integrate dCA from CA naught to CA. Again, CA naught is your initial concentration. CA is your concentration at a time T, is equal to K integral of dt from 0 to a time T. Integrate both sides. And if you don't remember, 1 over CA is ln CA, whatever it is. So I get ln CA divided by CA naught is equal to KT. And if you, let me just get the pen here. Let me just write the intermediate steps for this derivation. Sorry, where's this mouse? Oops. So basically, I'm gonna get ln CA from CA naught to CA is equal to KT from 0 to T. And this is basically gonna be ln CA minus ln CA naught is equal to KT. And from here, you get this final expression, okay? And this will be a recurring theme in many of the derivations. This type of, I separate the variables, I do an integration, I get some sort of ln and or logarithmic expression, and I do my separation. And this equation is called the performance equation, okay? Once you get to the performance equation, now we need to answer these questions. Does this equation fit well with all the experimental data I have? And you know, is my experimental data a straight line? And if so, what's the best estimate of K? So basically, if I want to test it, I would get minus ln CA by CA naught for my experimental data, and I plot. So you have your experimental points, whatever it is. So let's say you measure your experimental points, and you have your concentration versus time, right? And you have a table with all your results. So what you need to do now, we need to get a new element here. It'll be CA divided by CA naught. I calculated, so I'm dividing each one by CA naught. And then I'm taking the ln of this guy to get another thing, another element in this table. And then I'm going to plot minus ln CA divided by CA naught versus T. If my experimental data looks like a straight line, then maybe it fits case 1. Okay? So this is the logic when approaching these problems. Let me erase this mess here. But you know, just for your understanding. Okay. So at this stage, let me introduce a new parameter. Right? As engineers, we like to use we don't really like to use this concentration business, right? We like to deal with another parameter called conversion, right? This is what you'll see a lot in chemical engineering papers, literature, applications. So let's introduce this concept of fractional conversion, XA for a species A. And a fractional conversion is basically the ratio of reacted component divided by the initial concentration of this component, or initial number of moles. So in this case, XA is defined as NaO, which is your initial number of moles of A, minus Na, which is the final number of moles of A, divided by Na naught. So initial number of moles minus final number of moles, this is equivalent to the number of moles which reacted, right, divided by your initial number of moles. So again, your conversion is the number of moles reacted divided by initial number of moles. And if I do some algebra here, so if I this, I'll get Na naught divided by Na naught minus Na divided by Na naught. This is 1 minus Na divided by Na naught as by V to change it to concentrations. And again, we're assuming that the concentration the volume is constant. So if I divide this by V, I get the expression in terms of concentrations. Again, this expression or this expression is very important. You will need to use it a lot in your manipulations. So please be aware of this. You know, this guy right here, where it's basically XA is equal to 1 minus CA divided by CA. This is a very useful tool for you in solving problems. Don't forget about it. Okay. So so if I take the differential form of this, so I have XA is equal to 1 minus CA over C naught. If I take dXA, d of 1, you know, there's a kind of big constant number, so this goes to 0. I get minus dCA by C naught, and I get C naught is a constant because it's the initial number of moles. And you can also rearrange that dCA is equal to minus CA naught dXA. So if I move the CA naught to this side, minus CA naught dXA is equal to dCA. And if you integrate, you're gonna get CA is equal to CA naught to 1 minus XA. Or you know, if you don't even need to integrate, you just rearrange this guy. Okay. So these two expressions here, tools when doing mathematical manipulations and similar things. Okay. So if I try to rewrite case 1 using conversion instead of using concentration. So if you recall, my intermediate step at the top was dCA by CA, and I'm integrating it from CA node to CA. I'm going to replace the CA by this expression here. So I'm going to get integral, and then I'm replacing CA as well with dXA. So I'm rewriting this in terms of XA instead of CA. So I get minus CA node XA divided by minus XA CA node, and this CA node cancels, and this is equal to KT. Continue with the math. You get basically minus ln minus x is equal to KT. Right, and this is also an important equation when testing your data versus the conversion instead of versus the concentration. Okay, let me just do something here just so that everyone's on board. So what I'm doing is, dCA, I'm using this equation here, and CA, I'm using this equation here. So basically, I'm converting my integral from the variable CA to the variable XA. These two will cancel. So again, ln of 1 over 1 minus x is equal to minus, sorry, not integral of 1 over 1 minus x is equal to minus ln 1 minus x. And this will be from 0 to XA. And, ln of 0, ln of 1 is 0. So this basically becomes minus ln of minus XA plus ln of 1 and ln of 0. And this is how I get to this expression on the right-hand side. Okay, so now for case 1, I have two expressions. The first one in terms of concentration, second one in terms of conversion. And again, same thing, this becomes your performance equation in terms of conversion. And you need to check this equation versus your experimental data. And if you see that if I plot ln of 1 minus XA versus time, and I see it's a straight line and your experimental data is something like this, you might go, okay, so this is a first order reaction, which is unimolecular, and it's the data. And then I look at my slope to get the value of K. So again, this is case 1. And just looking at it, just reiterating what we said and comparing it to the experimental data. So I put minus n over XA or minus ln C over C university should get a line with the slope K. And of course, with real experimental data, you should expect some scatter, whatever it is. This is normal. Okay, case number 2. If you have an irreversible bimolecular second order reaction. And again, for this case, I'm assuming constant volume, constant temperature, and a set of products. Let's write the reaction rate equation for this. So again, first step, always write the reaction rate equation. Minus RA is equal to minus d by dt. And it's a one-to-one reaction, so A is equal to minus RB, which is equal to dCd by dt. And this is equal to KCA multiplied CB. Right, so this is the rate of consumption of A, the rate of consumption of B is equal to change of concentration of A by time, change of concentration of B by time, equal to K CA CB. So now we need to do, when we're using the integral method, let's say we have the experimental data for A, so I need to rearrange this in CA, right? So in order to do this, we're going to introduce a molar ratio, or introduce a new variable M. And M is equal to CB naught by CA naught, right? And the logic of introducing M is to make the math easier for us, so M is equal to C naught divided by C. The logic is, if I have experimental data in terms of A, I will need to C in terms of CA in order to integrate and separate variables effectively, right? So I introduce a new variable M, and then I'm going to rewrite the expression. So again, minus RA is equal to CA naught dXA by dt. And what I did here is, if you remember, what we said is, sorry, if you recall from the previous slide, we said CA is equal to minus CA dXA. So we're using this equation and substituting it here. So dCA is equal to minus CA naught dXA. So minus CA just equals CA naught dXA, which is expression here, is equal to CA naught minus CA naught XA. And I got the right expression from this here. So if you remember, we said XA is equal to minus CA divided by CA naught. So this basically is that CA is equal to CA naught minus XA CA naught, right? Which is right here. So I just replaced CA with this expression, and then CB, something very similar. So what I'm going to do is, similarly, we're going to say that CB is equal to CB naught. Sorry, let me fix this. oops. Sorry, CB is equal to, where it is, yeah, there we go. CB naught minus XB CB naught, right? XA CA naught, because this is a one-to-one reaction, and we're assuming it's unimolecular, right? Or it is unimolecular. So just to be careful, let me have a look here at your Levenspiel book, see if or at the book here, Levenspiel, see if they point out any special cases or any special things to keep an eye out for. So what's this, case 2? Yeah, because it's a one-to-one reaction, so this substitution is valid where CA naught XA is equal to CB naught XB. And the logic here is, if you want to really prove it, we can prove it where I can tell you that basically XB is equal to 1 minus CB divided by CB naught, right? So this basically means that CB naught minus CB is equal to XB CB naught. And this is the number of moles of B reacted when I compare it to this expression. So if I rearrange this expression, I'll also get CA naught minus CA equal to XA CA naught. And this is the number of moles of A reacted because it's a one-to-one reaction. So number of moles of A reacted is equal to number of moles of B reacted, which means that XA CA naught is equal to XB C naught. And this is how I made this substitution. Okay. Work it out by hand, see if it makes sense. It should make sense. If you're still having a hard time seeing it, come to us. Okay. Let's see here. And try to move a bit. Looking for laser point. Okay. So CA naught is equal to, basically I substituted my conversions here and I converted this expression into from concentrations to conversion XA. And when I do some math, so when I try to, or when I basically do some algebra, I can rearrange this expression into this form. And if you want, let's look at the derivation. So what I did here is if I take CA, if I basically take CA naught out of the first bracket, I get K CA naught into 1 minus A. And then if I take CA naught out of the second bracket, I get CA naught into C naught divided by CA naught minus XA. And if you recall, we said that M is equal to CB naught divided by CA naught. So I just put M here, and these two together, I get CA naught squared, right? So I get K CA naught squared, 1 minus XA multiplied by M minus XA. Okay, so now what I'm going to do is I'm going to separate them. So I'm taking these two guys, moving them here, and then taking the dt, moving it here. And CA naught is a constant, so you can actually cancel these two out. It's fine. And this becomes your expression. And then, you need to integrate this. If you don't remember how to integrate this, it's fine. You need to split it into partial fractions. If you don't remember how to do partial fractions, you should remember, try to practice it. Might show up on a test somehow, how to derive this. But basically the idea is on how to split things to partial fractions. So I have 1 over 1 minus XA into M minus XA, right? So if you recall from partial fractions, I'm going to say, I divide this into two fractions. The first one, I'm going to say A, 1 minus XA plus B, M minus XA, right? And when I combine them, I'm going to get A into M minus XA plus B into 1 minus XA divided by 1 minus XA into M minus XA is equal to this expression, or is equal to this expression. So from here, I can basically say that A, M minus XA, oops. Let me just erase this guy. There we go. To write slowly on this path. Okay, M minus, where's the pen? There we go. M minus XA plus B into 1 minus XA is equal to 1. So now I need to solve for A and B. So I take two cases, when when xa is equal to 1, because my variable here is xa, and when xa is equal to m. These are my limits of this fraction, right? Xa is equal to 1, xa is equal to m. So when xa is equal to 1, what do I get here? This guy cancels out. So I get a is equal to 1 over m minus 1. And then my other extreme case is when xa is equal to m. And in this case, I put m here, this cancels out, so I get b is equal to 1 over 1 minus m. Right, so I have two fractions. So if I split this into two fractions, I get my first fraction, 1 over m minus 1, 1 minus xa, plus 1 over m minus 1, m minus xa, and then I can integrate these two fractions separately, right? So just practice this partial fractions thing, make sure you remember it. This course will involve a lot of math, a lot of integration, derivation, partial equations. So, sharpen your tools, okay? You have to be ready to fight. Okay. Laser pointer, let's go back here. So I get this expression now, right? So I get 1 over m minus 1. Dx is a constant, so I'm just integrating this expression. And again, if you remember your integrals, so integral of, let me put it here, integral of 1 over 1 minus x is equal to minus ln 1 minus x. Similarly, integral of 1 over a minus x is equal to minus ln into 1 into a minus x, right? So I do my integrals. So again, this minus ln 1 minus x minus 1 minus m, and you plug in your limits, 0 to xa, 0 to xa, and this is what you get. Okay. 1 second, what's going on here?
Lectures for series
Other lectures playing. Let me keep this 1 second. Let me.
This is the part of week 2 lectures for.
Okay, sorry about that. Yeah, the other lecture started playing over this. So if you couldn't hear what I was saying is, just recall your integrals here. So integral of 1 over a minus x is equal to minus ln a minus x, and integral of 1 over 1 minus x is minus ln 1 minus x, okay? Let me change the pointer. Give me a second. Okay. So this is what we have. We did the integral, and we after you integrate, just remember always plug in your limits, and this is the expression you're going to end up with. You do some algebra, we're going to move things around, cancel things, do all of this stuff. You can figure this step out by yourself. This is the final expression we get, right? So this is your performance equation for an irreversible bimolecular second order reaction. You're responsible for this equation, responsible to be able to use it based on whatever information I give you, extract the missing parameter. Something to note, this expression is not valid for m equals 1. So for the case of m equals 1, it's equivalent to having 2a going to or reacting to give me a product and not a plus b. So in the case where I have 2a or equimolar starting mixture or equimolar 2 of one species going to a product, you need to use this expression instead, right? So again, just to recall, for case number 2, when I have irreversible bimolecular second order reaction, this is your performance equation where m is CB naught divided by CA naught. In the case where m is equal to 1, this becomes equivalent to 2a going to products, and this becomes the performance equation you need to use, all right? And this is just a look on how this equation performs. So again, when using this performance equation, I need to plot ln CB divided by CA versus time, and my slope will be this, or ln m minus xa, or m into 1 minus xa versus time, and my slope will be equal to this. All right, and again, CA naught should not be equal to CB naught. for the case where CA naught equals CB naught, i.e. M equals 1, your fit becomes different because you're using a different equation in this case. Okay, let's move on to case number 4, nth order. So sometimes you have no idea what order it is, right? You have the data, they look weird. You don't know, it might be like a 0.6 order or 2.5 order, something in between, right? So if that is the case, this becomes your starting format, right? Minus RA is equal to minus dCA by dt is equal to K CA to the power n, where n is an unknown for you at this point. So if I separate my variables, so I move this guy here, move this guy here, I get dCA divided by CA to the power n is equal to K dt. And if you integrate it, you get this expression, right? And when using this expression, you have to be careful. For first order reactions where n equals 1, you need to use case 1. You don't use this equation at all. Where n, if n is not equal to 1, then we need to use this expression and we do a set of trial and errors until we find the value of n which matches our experimental data. Okay, this is important to know. For the case of zero order reactions, again, zero order n is 0. So this equation really reduces to something very simple. Becomes Ca minus Ca naught is equal to minus Kt, or Ca naught minus Ca is equal to Kt. Basically, Ca is equal to Ca naught minus Kt, right? So for a zero order reaction, your expression is very similar, and you can use this expression to test against your experimental data. One thing to note about zero order reactions, and you have to always remember this when looking at experimental data for zero order reactions, is that mathematically Ca can never be less than 0, right? Your concentration can never be less than 0. So the lowest value for Ca in this case is 0, which means that your T has a limit, a maximum limit. You know, so if Ca is 0, so I get 0 is equal to Ca naught minus Kt, and 0 means complete consumption of A, right? So I have A, zero order reaction, A is completely consumed, final A is 0, my initial is here. So the reaction time, or the maximum possible time, is usually denoted T max. This is equal to Ca naught divided by K, right? This is my maximum possible time for this reaction. Something to remember when dealing with zero order reactions. Another thing to remember when dealing with zero order reactions is that when you're measuring experimental data for zero order reactions, you will almost always see a deviation at low concentrations, right? So at low concentrations here, there's always a deviation. And you need to be aware of this, that if you're plotting a straight line, this straight line, as I approach 0 for concentration, will stop fitting. So you might be tempted to try and look for another order to try and fit this curve, but this is fine because mathematically your experimental data will always deviate at low concentrations. Similarly, math is no longer valid. This is what the slide's saying. Similarly, if you're plotting your data in terms of conversion, so on my right-hand side here, you can see that at very high conversions, so basically as Ca gets to 0 or completely converted, my experimental points stop adhering to this straight line type of format, and I get a deviation. So I might be tempted to try and fit it to a curve like this, but if it's a zero order reaction, you just need to be aware that this deviation is normal. Now we have other errors being introduced, you know, other effects like start becoming very high, so you start getting deviations. Okay, so now let's introduce a new parameter called reaction half-life. And this is a useful concept because it makes a lot of your calculations much easier, because you can always just look at this equation and use it directly, right? The half-life is the time it takes for the reactant concentration to reduce by a factor of 2. So basically the time it takes for Ca to be 0.5 Ca naught, right? Time required for half your half your species to be consumed. And the equation used to calculate the half-life is this: T half is equal to 0.5, 1 minus n minus 1 divided by k into n minus 1, Ca naught into 1 minus n. And you might be asked to derive this. So if you want to derive this, you look at this equation, you set Ca naught, you set Ca to be 0.5 Ca naught, and you just calculate your time, right? So if I just set Ca is equal to 0.5 Ca naught in the previous expression, solve for the time, I'm gonna get my half-life. And in some labs, for example, you might get data in terms of T half versus ln T half versus ln Ca naught, right? So sometimes, especially in research, they like to run isothermal experiments at different values of Ca naught, and they just plot ln T to the half versus ln Ca naught. Because usually it's easier to measure the time when your concentration goes to half versus measuring every concentration versus time, right? And these are the types of plots you see. So if order is less than 1, the plot of ln or log T half versus Ca naught looks like this. Order greater than 1, it looks like this. And if the order is first order, it's just a horizontal straight line. Something to know when it comes to analyzing data. However, this equation 33a is important for your calculations. All right, so let's move on to the final few cases here. Case number 5, which is autocatalytic reactions. So what's an autocatalytic reaction, right? An autocatalytic reaction is a reaction in which one of the products acts as a catalyst for the same reaction, right? And sometimes they're referred to as runaway reactions, autothermal reactions. This is a similar type of autocatalytic reaction, etc. And as you can see here, A reacts with R to basically make more R, and then this R catalyzes this reaction further to make even more of the product R, right? So this is a reaction type out there. It's common. You'll see it in polymerization, maybe pharmaceuticals, other types of applications. So in terms of stoichiometry, it's the same. So this is equivalent to A going to R, right? So even though this is the elementary expression, this is what actually happens. Stoichiometry, from a stoichiometry perspective, this is just A equal going to R, right? But again, this is one of the cases where stoichiometry does not represent what actually happens. However, the rate depends on the concentration of R. So if I want to write the reaction rate, it will be minus dCA by dt is equal to kCA divided by CR. And the reaction will never start unless some R is present. So obviously, it's like having a polymerization reaction where you just introduce a small amount and then it starts generating more of the same species. And here we'll go through the derivation to get the expression. Total number from the same procedure as the previous ones, and you're only responsible for the final expression in this case, but it's good to look at the intermediate steps. Because the total number of moles of A plus R remains constant, just a basic balance, C total is equal to Ca naught plus Cr naught is equal to constant. So I can rewrite Cr as C total minus Ca. Because if I'm using the integral method, I want to separate the variables. So if I have dCA here, I need to rewrite this as a function of Ca somehow so that I have the same variable everywhere. So I write an overall balance where I say my total number of moles is just equal to the number of moles of A plus the number of moles of R. And my total number of moles will be constant in this reaction because just 1 plus 1 will give me 1 plus 1. So my overall number of moles should be fixed. So if I do this and I rewrite my expression here using C total, which is a constant, I get this expression. And then once I get to this step, I can separate my variables and do my integration, which is what you see here. And again, this is one of the other ones where you do partial fractions and things like that. You can try it and you'll get the same answer. But however, the final expression is this, where I basically get ln of a big expression where I have two constants, Ca naught C total, divided by Ca multiplied by another constant. And this is equal to C total Kt equals Ca naught plus Cr naught Kt equal to ln this ratio of CR node, CA, right? So this is the performance equation for an autocatalytic reaction, right? For the autocatalytic reaction. And again, when solving problems, you'll probably not see this as much as the other cases. And these are what the curves usually look like for autocatalytic reaction. There's something for you to, know if I have a hysteresis curve of conversion versus time, then it is an autocatalytic reaction. If I have a parabolic curve of reaction rate versus, concentration, then this is also an autocatalytic reaction. All right, case number 6. First order reversible reaction. Again, this is the reaction I have A going to R. It's a first order, and it's the only difference now from case 1 is that it is reversible, right? And our assumptions are the same: constant volume, constant temperature, and elementary reaction. So I have A going to R. The forward constant is K1. The backward constant is K2. So if I write my reaction rate expression, this is what I'm gonna get. So again, we also introduced this parameter M, CR node divided by CA node, and this is just to make my algebra easier. So let's look at my reaction rates. dCr by dt, this is a plus here because it's a product, is equal to minus dCa by dt. This minus is because it's a reactant, is equal to CA node dXA by dt. And what I did here is I just used this manipulation, if you recall. We said, dCA is equal to minus CA node XA. And again, you're gonna use this a lot. It's gonna make your life easier when doing this algebra. So dCA by dt is equal to CA node dXA by dt. And this is equal to basically the reaction rate from this reaction. So for CA, the rate of, or let's say for CR, the rate of production of rate of production of R is equal to K1 CA minus the rate of consumption of R, which is equal to K2 multiplied by CR, right? So this is your forward reaction, and this is your backward reaction. And when having reversible reactions, you always have two expressions, right? One for the forward, one for the backward. And again, similarly, I'm gonna substitute. So if you recall, we said CA is equal to CA node into 1 minus XA, right? So I'm gonna substitute this guy here. So I get CA node minus CA node XA minus K2, and then M CA node plus CA node XA. And this is similar to the manipulation we did earlier, where basically I'm saying CR, fix this around, do this. Okay. Let me erase. And sorry, so I get basically CR is equal to CR node into 1 minus XR. And because it's a one-to-one reaction, so, CR node XR is equal to CA node XA because 1-to-1. So basically I get the expression of CR node minus CA node XA. And CR node is equal to M multiplied by CA node. So I just replace it here and I get this expression, okay? Once I get to this point, I need to do some separation of variables. So note that at equilibrium rates are 0. So in the special case of having equilibrium rate expressions of 0, I get CRE divided by C reference, CAE divided by C reference, and this is equal to K1 divided by K2, right? So this is a very special case where your equilibrium reaction rates are 0, right? And Sorry. Okay, going back to the lecture. Um, sorry, so we're looking at the first order reversible reaction, A going to R. We derived our expression here. So at equilibrium, you need to realize that because it's a reversible reaction, if you remember from your chemistry, at equilibrium, dCA by dt equals 0, right? So at equilibrium, the forward reaction is equal to the backward reaction. So the rate of change of number of moles of A is equal to 0. You have an equilibrium concentration of A always present. So if I set dCr by dt equals to 0, and I rewrite this expression, this is what you're going to get. So basically, you get that K1 divided by K2 is equal to CR naught plus CA naught multiplied by XAE, where E here refers to equilibrium, right? E refers to your equilibrium conversion, and again, here is your equilibrium concentration as well, right? So you just have to be, and of course these cancel out, so it doesn't matter. You just have to keep an eye on this type of expression because it's a reversible reaction, sorry. So you'll always have an equilibrium point, right? If you recall Le Chatelier's principle and these things, you can push the reaction forward, push it backward, whatever it is, but it will sit at a certain equilibrium where you have equilibrium concentrations, fixed concentrations at all points. So because equilibrium rate is 0, this is the expression I get. You can combine 1 and 2, do a bunch of algebra, separation of variables, whatever it is, and this is the final expression you're going to get. So for this case, you're only responsible for the final expression. So if I tell you you have a first order reversible reaction, this is the equilibrium conversion, this is the M, this is whatever, find the time, you plug into this equation and you use this and you find the missing parameter. Okay, so again, this is your performance equation. Your exams will be open notes, of course, open books, whatever it is. So you have to be able to locate it, you have to know what these represent, and you have to basically plug in the numbers and solve using your calculator, whatever it is. And again, the reversible reaction is simply a special case of the reversible reaction in which your your equilibrium concentration is equal to 0, or your equilibrium conversion is equal to 1. So you can match this with previous case, which is case 1, I think, case 1 I recall, just by doing some algebraic manipulation. So they're all related because they all have the same root, and you can do your algebra to make them all match each other. Okay. And again, this is what you plot for a first order rate equation, and then for a reversible reaction, then you compare your experimental data to your performance equation, and if it matches, then this is the right case you're looking at. Okay, let's look at case 7, second order reversible reaction. And again, we're assuming constant volume, constant temperature, elementary. And if you have a second order reversible reaction, it could be any of these forms. So I could have A plus B going to R plus S. I have 2A going to R plus S, 2A going to 2R, A plus B going to 2R. Whatever it is, CA naught has to be equal to CB naught, and CR naught is equal to CS naught is equal to 0. So my concentrations of my reactants are equal, and my initial concentrations of my products are 0. So this becomes your performance equation. You can look at Levenspiel if you're interested in the derivation, but we're more interested in the application of this equation for this course, right? So you need to be able to look at this equation, plug in the parameters you have. So if I tell you the equilibrium conversion is this, or the equilibrium concentration is this, you can calculate the equilibrium conversion. You're given some parameters. Usually you're asked to calculate the time. So you should be able to manipulate this expression to get to your time. Okay. And of course, again, going back to the same point, we're trying to fit some experimental data. So this expression, so if I plot ln, this expression versus time, the slope should be equal to 2k1, 1 minus xae minus 1 ca naught. Good. And then this is our last case here. And we're not going to derive any numbers for this case. This is something you just need to be aware of. sometimes when doing experiments, you notice that there are reactions of shifting order. And what this means is that even though you say running a reaction goes A goes to R, but my reaction rate expression looks something like this: K1CA divided by 1 plus K2CA. You see this a lot in catalysis. So if you take a catalysis course, you'll learn how to derive these expressions. And so for this case, when Ca is very small, so if Ca is very small, it's a first order rate reaction with coefficient K1. When Ca is very large, then it's a zero order reaction with a rate of K1 divided by K2. So you can see that your order of your reaction changes significantly with your concentration. And this is called the shifting order reaction. And these are common in biochemical applications, and they're also very common in catalysis. So this is just something for you to remember off the back of your head. And this is what they look like experimentally. So Ca versus time, we'll find out that you have a very clear linear slope and then changes significantly. And as you can see, this is far away from C equals to 0, because remember we said that if I have a zero order reaction, my points could look like this, but I see this conversion very close to the 0 point. But for a shifting order, you can see a clear shift of order halfway through. Similarly, if you're plotting your reaction rate versus your concentration, you can clearly see a shift of the reaction rate order here as well. Okay, and yeah, there are other ways. If you don't want to plot Ca versus time, you can always plot your ln and get some type of, to get a straight line to make your analysis easier. Okay, so your Levenspiel chapter, or the chapter you posted for reading, you also have reversible trimolecular reactions, reactions in parallel, homogeneous catalyzed reactions, all types of things in series, all this stuff. You can always read them to try and learn more. I highly recommend that you read through example 3.1. And you can always look at the differential analysis and varying volume batch reactor. However, we don't have time to cover them in this course. So let me recap. So what you need to know for this course, especially you need to know how to use the equation for case 7. So you need to know how to use equation 56. You need to know how to use equation 54, not derive them, just use them. So if I tell you I have a second order reversible reaction with these parameters, get me the time, you need to be able to find the right equation to use, plug in the numbers and use. If I tell you I have a first order non-reversible reaction, you need to go to case 1, find the right equation, use it. So the application will mainly focus on the performance equation. Autocatalytic, I'm not gonna ask about this a lot. Reaction half-life, you should be familiar with this equation and be able to use it when needed. Nth order reaction, this equation is also important for you. Should be able to know how to use it, when to use it. Let's have a look here. And again, case 2, the two cases or the two equations for case 2. The first one is when m is not equal to 1. And you should also be able to use this when m is equal to 1. And finally, case 1, which is the absolute basic one here. Oops, where is it? This equation, you should also know how to use it. Okay, so this is the end of lectures for the kinetics lecture in week 2. We're covering chapter 3 in Levenspiel. The slides are posted, the lecture will be posted, the book chapter is posted for your reference. I've also posted the homework. Please upload your homework on the due date, which is before next week's lecture, and the video with the homework solutions will also be posted. Thank you very much.